Hi, I'm Jason Hildreth, and this is the presentation for my term project for IME222 Engineering Graphics Lab. I designed a wingtip vertical takeoff and landing assembly for an RC airplane. I chose this because I plan to use it for my senior design project if it fits the mission type when that time comes. So to go through this video, I took your requirements that you listed up here, and then I turn that into this checklist down here, and we'll just go through that. All right, the first thing on our checklist says explain the steps you took to produce the assembly. So let's look at the assembly. Here it is. This all started with choosing a servo motor that was going to drive this that would be powerful enough. So I chose the servo motor. I modeled this just as the case and the drive shaft, because those are really the only two parts that mattered for this project. I needed to keep this aligned with the rest of this assembly so that this gear would stay aligned. So these mounting lugs I created to attach on the back with pretty tight tolerances on their location so that they align this servo motor shaft directly in the middle of this pass-through. That pass-through gets us to the drive gear. This drive gear is made with an involute gear profile. The involute gear profile was done by hand sketching instead of, well, it was done mathematically sketching instead of just guessing at what a good gear profile looks like. So all of these circles here are the main circles that you need for a gear. There's the outer diameter, the base circle, the addendum and the dedendum, and the pitch diameter. All of these construction lines that you see here are equally spaced angularly so that as they intersect the pitch diameter, we create a tangent line to that circle right there, which is our pitch diameter. So as one of these radial construction lines passes it, at that point you generate a tangent line. The length of that tangent line needs to be the distance between where one of these intersects and where the other intersects. So I just made a line between them and made this equal to it. Once you have that, the next time that one of these intersects, you make another tangent line that is twice as long as the previous one. Next time it intersects, you make a tangent line that's 3 times the length of the first one. The next intersection, you make this tangent line, which is 4 times, then this one that's 5 times as long as the first one. And you connect the ends of all of those with a single spline. That is this spline, and that defines the involute gear profile that we need. So we take that, and the bottom part of this is really inconsequential. This isn't where the teeth of gears actually interact. This is just to make a nice smooth transition between gears that goes down to our base circle's radius. So we take this profile, we mirror it across this line to get one full tooth. We smooth that into our base circle there. We extrude that pad and we radially copy it the number of times that we need teeth. That's how we get the drive gear. Similar things were done to get the output gear. This gear only needed, I think, 11 teeth, and that's because it was not going to have to rotate the entire 360 degrees. This is only going to have to rotate about 120. So let's bring up the sketch for that one. We're in the wrong part. Single tooth profile. So again, this is done basically the same way with the same setup. So I generated an entire gear from that instead of just generating the 11 teeth. And then I modified that to have the hole in the center the size that I needed it, the other pockets. And then in these other sketches, I'm making more delicate adjustments to the shape of this thing. So we'll look at some of these adjustments in the next section. That just needed to attach to the DC motor mount, which is just a 90-degree angle bracket with recesses back here for the hex bolts to recess into. And now I think we can move on to the next part of the checklist. All right, that covers explaining the steps I took to produce the assembly, and now we will look at the compromises made to the design when modeling in 3DX. There weren't a whole lot of compromises due to the software. It was more just things that I hadn't thought through enough when I started putting this together. Mainly how this outer plate was going to attach the cover. So as you can see, I ended up having to have two bosses that stand out from the back plate. These allow us to put the screws in and attach without interfering with the gears. But this output gear would have interfered with that tooth. So if I had just left it as it was, this whole output gear being all the teeth, I wouldn't have been able to put this here. I would have had to find a different way to attach this, and it probably wouldn't have been sturdy at the front. So instead, what I did was I took this output gear and I used it as a limit stop for the rotation. We only want this mechanism to rotate so far, and we can program that into the flight control system. But in case there's some sort of error with the flight control system, we don't want the propeller to smack into the rest of the airplane. So this boss actually acts as a physical limit. When this gear rotates in this direction, this section will bump up against the boss to stop it. And in the other direction, this cutout from the gear will do the same thing in the other direction. So if we were to take it here and rotate it, and it doesn't seem to want to do it right now. We're going to have to reload 3DX to get that to work probably. Yep. So we'll look at that in a minute. But that was one of the things that I had to work around was where do I put the screw placements to not interfere. That also happened back here with the servo motor, or I'm sorry, the DC motor. These countersink screws I had assumed were a little bit longer than they actually could be, and they were going to interfere with those copper windings. So I had to shrink those a little bit to make sure that I had the right hardware to not interfere. Similar thing happened on the back here. The mounting hardware for these gears, this mounting hardware, this little screw, is actually starting to interfere with the housing. And if we can get a good view of it here, you'll be able to see that we just have a little bit of clearance with this plate and the other screws. So not a whole lot of clearance, but if our tolerances are good, these aren't actually going to overlap. There's just a little bit of clearance. So you probably use screws with shaved heads, but I didn't model shaved head bolts. But they do have clearance right now. That is just one of the little details that had to kind of be revisited as I got deeper into the modeling. Otherwise, the software was good when it was accessible. I'd say that the biggest compromise that I had to make was with my schedule to find a way to get access to 3DX, because that was a little bit difficult this semester. All right, on to the next part of the checklist. All right, that covers the compromises on 3DX. Now for the fun part, the engineering connections that were used in the project. Most of this is rigid connections with a couple of Revolute connections. and one gear connection. So if we if we bring this up and scroll to all the fun stuff at the bottom, most of this is all held together with rigid connections. It shows it there. This doesn't end. There we go. Refresh all of these and show them updated and functioning. It doesn't update there. All right. We will take this Revolute connection, which is between the drive gear and the housing, and this Revolute connection, which is between the output gear and the housing. And those are the two connections that we use to define our gear connection, which is down here. Here's the compound connection. That will show that it is between the two axes. I'm sorry, the two planes relative to a center line running through the main case. So it is a plane-to-plane interaction that causes these revolute interactions to work at a ratio of 2 to 1 because that's my gear ratio. So that is that connection. A similar connection, as far as the revolute connection goes, was used to put the front and back sections of the DC motor together so that they are able to rotate relative to each other. And again, everything else is pretty much held in place. We didn't want things to really move around, except for the couple of things that we need to move. So that was done, and this is going to look terrible, and I apologize for how this looks, but that was done by adding an extra line to the face of everything I'm going to need to line up, which is why we have all of these extra wires sticking off of things. Each part has one running along any rotational axis that it has so that I could line up axes easier in the engineering connections. And then they also have another one along one of their orthogonal faces so that I could use that as an angular reference between that and another part's face to prevent rotation. So that's how I made the rigid connections. It was usually a concentricity of an axis, will lock on the angle between a line on each face, and a contact or an offset to hold it along that line at a certain position, and that will create a rigid connection. The ones that I didn't want to be rigid connections were the motor shaft inside the servo here. So the connection between the servo motor housing and the motor shaft is a revolute connection. The other ones that are revolute connections are going to be the gear here. That has a revolute connection associated with the bracket. Actually, no, it has a rigid connection with the bracket. The bracket has a rigid connection to the motor shaft. The motor shaft is the one that has the revolute connection. So they're all based on that one revolution. On this other side, these all have a concentric axis running through the center that the bolt runs through, and that is the axis of revolution for this assembly. Other than that, the hardest part was getting the gear interaction to work when I was trying to use lines instead of planes to define their action. Sometimes negative signs in the gear ratio fixed it, sometimes it didn't. I could reload it and it would work different the next time. So we had to switch to planes. And those are the engineering connections that we used on this part of the project. All right, one more time back to the checklist. That's the engineering connections, and now we get to do the video animation of the model. So let's go in here. We've already hidden the front cover. I'm going to go ahead and put the robot on the servo motor and begin rotating that. That'll allow this gear to rotate the other, get it up into position for vertical takeoff. And if we continue, if you look down in this corner here, you'll see where that gear will eventually butt up against that screw boss. That is our backup for our limit on rotation in that direction. And if we rotate this the other way, ooh, it jumped a little there. Slow it down. If we keep going the other way, you'll see that the angle bracket actually becomes the stop. So right here, the angle bracket has contacted the edge of the screw boss. So that's our stop. It also shows the animation for how the gears interact with that revolute connection and the gear connection. The same thing works with our DC motor here. We can put the robot on the outside part of the case and it will spin relative to the inside. The shaft is actually attached to the outside, so it is actually spinning along with the rest of this right now. And those are the animations that I am able to produce with my model. So let's go check that off. All right, that is the end of the animation, which is the last thing on the checklist for make a video recording. So I'll make this easy for you, and I'll just go ahead and grade that real quick, and hope you have a great Christmas. Thanks.